Welcome to UGC lecture series in computer science. In this lecture, we are going to discuss about paging as a solution to external fragmentation. What is paging? Paging is a scheme where the memory addresses are divided into fixed sized partitions and stored in a same sized blocks. The actual data or instructions which are to be read from or written into the memory are actually carried through pages. Therefore, pages having the same sizes throughout the memory are easily manageable and accessible for the operating system. Paging involves translation of logical address to physical address, which we refer to as address translation. In paging, the logical address space of a process can be non-contiguous. It can be in bits and pieces distributed over the entire storage area. Every process is allocated one particular storage block or many such storage blocks in the real physical memory whenever the physical memory is available. Therefore, until the physical memory is available, the pages or the block of memory retains the information in the temporary storage area, which is accessed and referred to by logical addresses. The scheme of address translation involves the access to logical address and its translation to physical address. Paging is actually implemented by a special hardware called paging hardware. In paging, we are actually dividing the physical memory into fixed sized blocks, and logical memory is also divided into fixed sized blocks. However, physical memory is the blocks in physical memory is referred to as frames. The blocks in logical memory is referred to as pages. The contents in the pages are written into the frames during the write operation, and the contents from the frames in the real physical memory is written back to the pages during the read operation. However, the read and write operation both involve the address translation from logical to physical address, which is implemented by the paging mechanism. Pages are generally in terms of powers of 2, that is between 512 bytes and 8192 bytes. This is the fundamental level of implementation of paging scheme in any operating system. Modern days operating system also implement a complex variety of paging, which is referred to as inverted paging. This will be discussed at the future episodes. Operating system always keeps track of the total number of frames available in the memory and the number of free frames out of the available frames. Therefore, whenever there is any requirement for associating the blocks of memory from the physical area to the logical area, the paging hardware takes care of the address translation and reads from or written to the data in terms of bytes. So, operating system is the key part which actually keeps track of the paging mechanism. To run a program of size n pages, the operating system needs to find n free frames and load the same program. Therefore, you can understand the relativity between the pages and frames. Pages are logical, frames are real, which are available in physical memory. The same amount of information in frames will again be loaded at the same amount of storage area provided by your pages. The only difference is that the location where the frames are available is real, and such locations will have heavy memory addresses which are of too many bits. Such memory addresses really can't be used for calculation with the address translation mechanism done by the CPU. Therefore, we map it to a logical area called pages. This is actually done by setting up a page table. This page table makes the correspondence between every page and the frame available inside your paging system. This page table also has a register called page table base register and page table length register, which are used to calculate the size of the page tables. Here comes the problem of internal fragmentation. As you can remember, internal fragmentation is something which arises out of the over allocation of storage area for a particular process. Assuming a process requires 50 KB of size for its entire processing, among the 50 KB, there may be the program segment of the process, data segment, extra segment, everything would be there. Assuming the data segment is allotted 15 KB out of the 50 KB. But in reality, at the start of the process, this particular process may only have 10 KB sized data in the allocated area. Therefore, out of the entire 50 KB, only 45 KB would be really used by the process initially. The extra 5 KB is allocated in anticipation that the process would use the memory area and grow in size as and when it executes the entire, as and when it performs the entire processing. However, it may so happen that this particular process will never use the extra allocated 5 KB. Therefore, this 5 KB of memory out of the totally allocated 50 KB will anyway be waste. Assuming there are n processes wasting 5 KB each, collectively this may come together as 1000 KB sized block or 2000 KB sized block. However, this 2000 KB or 1000 KB are actually distributed in bits and pieces of 5 KB each all over the memory, so that they will never be utilized fruitfully for any other processes. Therefore, this internal fragmentation is a major problem in the paging scheme. The only solution to internal fragmentation is allocating the sized memory blocks as and when required. But the problem is, when the process is really allocated a 45 KB and when it desires to grow out of the allocated area, it should first request the memory area. The memory request should be then interrupted by the entertained by the operating system by releasing an interrupt, and the memory request should be allocated to the particular process, and assuming it is asking a 5 KB and assuming if there is only 2 KB right now available, this process will never be able to continue its processing. This process would have to be stalled or postponed for a later time. Therefore, the implementation of variable sized pages is actually a challenging problem. But in modern day operating systems, these variable sized pages are also used in picture. More discussions on variable sized pages is postponed to the later sides of the later portion of this particular lecture. Address translation is the fundamental thing for which this particular paging is being designed out. In address translation, there are two things to be taken care of. There is a logical address which is generated by your CPU. In this logical address, it is basically a series of bits, and among the bits there are two divisions or logical divisions which we have to understand about. There is a segment called page number and there is another segment called page offset. Assuming there are 16 bit, the addresses generated by the CPU is of 16 bit, 8 bits would be the page number and the remaining 8 bits would be the page offset. Among this, the page number always would be at the higher order level and the page offset always would be at the lower order level. Lower order in the sense, among the 16 bits, bit 0 starts from the right extreme, therefore, bit 0 to bit 7 forms the page offset and bit 8 to bit 15 forms the page number. Therefore, every page addresses logical addresses of size 2 power m and page size of 2 power n is basically understood in terms of P and D. P indicates the page number and D indicates the page offset. Page offset combined with the page number gives you the real logical address. The calculation of page number and page offset is actually as follows. If the page size is 2 power n, n bits would be allocated to a page offset and m minus n bit would be allocated to the page number out of the total logical address space of 2 power m. The address translation scheme inside your paging actually goes this way. Here is the CPU which is generating a P and D, page number and page offset. The combination of P comma D is basically the logical address. Remember, the logical address is a sequence of bits only. We actually visualize the logical address out of two parts, P and D. The D part or the D portion of the logical address is retained as such and the P portion of the logical address is which is indicating the page number is taken and is given as input to the page table. Page table is a real hardware which carries the information or correspondence between the pages and frames. Assuming here is the physical memory, in the this is the real memory available and the fixed sized blocks here are called as frames and the fixed sized blocks in the logical addresses are called as pages. Pages are denoted by P and frames are denoted by F. Therefore, in the page table there is a correspondence between every P to every F which is maintained here. In the page table, this is a simple page table, therefore, in this particular page table, every entry in the page table is basically consisting of the frames. If you take P from this particular logical address, the P actually would be calculated as a displacement or the distance between the start address of the page table to the corresponding available frame. This particular area or distance is referred to as P. Therefore, if you take P, you have to cross these many addresses and then you have to identify that particular frame which is mentioned in the page table. It indicates that this particular page is actually available in the this particular frame number F in the physical memory. Assuming you have identified now the frame number, now the problem is to identify the real address inside that particular frame. I have already told you a frame is of size, fixed size, therefore, assuming every frame is of 5 KB, in 5 KB there will be too many addresses available. Which particular address in that 5 KB frame tells you, gets you the data or gives you the data, you have to identify. Therefore, we take this F and we have already the displacement D available as the second portion of the logical address. Along with this D, you add this F, the remaining the address which you get is called as the physical address. Therefore, the address which is indicated by adding the F, translated F to the displacement T gives you the real address and where it points to that particular area in the physical memory tells you the information which is actually needed. This is the address translation mechanism of the paging scheme. Therefore, the CPU generated logical address is getting converted to physical address and the memory access is now made. So, this is an example of a paging model. Here is the logical memory, here is the physical memory which is containing the frames and here is the page table. Page table has entries, 4 entries and the page 0 has the entry the entry 0 in the page table has 1. 1 actually indicates the area of the frame number. So, if f is equal to 1 and this is the area of your physical memory, you start from counting 0, 0, 1, 2, 3, 4, 5, 6, 7. There are 8 frames available and the page 0 is in frame 1. Therefore, the frame number of page 0, the frame number 1 is actually stored in the page table. So, this is how the frame numbers are getting translated and previously stored in the page table, so that at any later time the CPU, when it wants to access the frame, it just scans the page table and goes for the accessing the frame number. This is an example of paging. Here this example tells you gives you a 32 byte logical memory and a 4 byte frame. This is actually similar to the one we have discussed previously. Here, assuming this is the frame, every frame has certain sequence of addresses. Here this is the second frame, frame 0, 1, 2, 3, 4, 5, 6, 7. There are 7 frames and every frame has set of 4 addresses. The second frame has IJKL address. Therefore, in this page table, the first entry has a frame number 5. Assuming the frame number 5 is 0, 1, 2, 3, 4, 5. 5 is the frame, this particular frame. Therefore, whatever entry from this particular frame is actually indicated by this entry. We can refer to here, the 0 is actually mapped to the frame A. A is available in frame number 5 and therefore, the 0 is corresponding to the frame number 5 in the page table. OS also keeps track of free frames which are available inside your process. Assuming these are the free frame lists in these examples, 14, 13, 18, 20, 15 are the free frames available. You can refer to the figure. It is not in order. In figure, it is 13, 14, 15 only, but the list of free frames are actually saved in terms of the order of frames which were made free. Assuming the 14 was made free at a much later time, at a time much before than 13, and after 13 is made free, 18 is made free, and after this 20 is made free, and after this 15 is made free. This is the free frame list status before allocation. After allocation of the page, from the figure you can identify 13 is allocated to page 1, 14 is allocated to page 0, 18 and 20 are also allocated, and 15 is the free frame. You can see the allocation, and the page table now has 0 has 14. 0 means the page 0 is actually in the frame number 14, which is indicated in the figure. This is how an operating system takes care of and maintains the free frames available. The implementation of page table is basically done by 2 registers, PTBR called page table base register, which indicates the start address of the page table, and PTLR called page table length register, which indicates the total length of the page table. With these 2 registers, the entire paging mechanism is implemented. In every address translation scheme, it is actually consisting of 2 memory accesses, one for the page table and another for the data and instruction. The problem is how to reduce these memory accesses. Can you reduce these memory accesses? If you don't use page table, there will be n memory accesses for accessing n frames. However, there is one solution given to the reduction of memory accesses in terms of associative memory or translation Lookaside buffer. This is basically a hardware kind of implementation, which is basically a cache memory. In this cache memory, we actually store the correspondence between a process and a frame, and which is used for address space identification. This is how the associative memory is. There is a correspondence between every page and frame which is directly stored in the registers, and a parallel search is done between a page and frame pair, and if the P, F pair is not identified, then the access to the page table is done. This is the paging hardware we are implemented with the associative memory, or otherwise known as translation look-aside buffer. Here is the CPU, it is generating the logical address. We visualize the logical address as P, D. D is as usual kept aside for later use for adding with the frame after getting identified. Now our process is to identify the corresponding F for this particular P. In normal paging, this P would directly be referred to the page table and F would be generated. However, this is the associative memory, a hardware implementation of paging. Therefore, this P is first taken, and this is the associative memory, which is a register which houses the page comma frame pair. Therefore, a parallel search I mean however many locations may be available in this TLB, every individual location is not searched sequentially but parallelly. Therefore, for a single memory access, the entire TLB is searched for a corresponding F for this particular P. If a corresponding F is identified, assuming in this location the P comma F is available and the F is identified, it is directly given to this particular adder, and this adder adds the F and D and the physical address is generated. If there is no correspondence in the associative register, then there is a fault getting generated. This is an internal page fault. Therefore, the paging hardware handles it back again and gives the P to the original page table and gets the frame. Therefore, a hit would go this way, a miss in the associative memory would go the original way. This is how the translation look-aside buffer is implemented for reducing the memory access inside paging. Because this is a hardware, the speed in accessing the hardware gives you the frames more faster than the original paging scheme. The effective access time is they now calculated as follows. Assuming the hit ratio is indicated by alpha and every associative lookup takes sigma time unit, the hit would actually be written as 1 plus sigma into alpha. Sigma is the lookup, associative lookup, and it is added with 1, that is, it is to start the associative lookup table 1 memory access time plus to search the entire table sigma access time into alpha. Alpha is a hit ratio. This 1 plus sigma into alpha gives you the hit ratio for addresses P comma F pairs found in the associative memory, and if there is no correspondence found in the associative memory, this is actually a miss. Therefore, a miss would take one more access to page table. Therefore, 2 plus sigma into, because this is a miss, out of the total memory access time you have to minus this alpha. Therefore, 2 plus sigma into 1 minus alpha. You calculate this, you finally get this answer for effective memory access time, 2 plus sigma minus alpha. This is basically indicating the percentage of hit and miss when associative memory is used. Memory protection is a mechanism which you have to take care of as a solution to the hit and miss problem inside your associative memory. However, entries are there in your associative memory, the associative memory is bound to give you not a permanent solution but a temporary solution to the speedy access for translation of P to F. Therefore, memory protection mechanism is introduced. In this mechanism, along with the correspondence of P comma F pair, there is a third column which indicates whether the correspondence of P and F is a valid correspondence or invalid correspondence. Valid indicates that it is still the P comma F pair is currently used by any other process inside the process list, and invalid indicates that the P comma F pairs were used previously and right now nobody is utilizing the P comma F. Therefore, the operating system might look at the I indicates the invalid bit and utilize this particular area to store more new frames, and then only at a later time it will come for replacing this particular valid bit indicated frame. Therefore, this valid and invalid bits are actually pre-written when every frame is actually formed or getting an entry inside a page table. After a particular process which is accessing the frames leaves out of the entire operating system on its total completion of execution, the valid bit V is changed to invalid bit, so that in future any new process can utilize this memory area and restore its particular frame over this particular area. And here comes the mechanism of shared pages. Because the valid and invalid bit mechanism is available in the page table, people guessed, what if there would be one particular memory area which is going to be shared by more than one processes. However, the implementation of shared page tables using a valid invalid bit is still more challenging. In shared pages, there are two variations available. The code may be shared or data may be shared. If the code is shared, the problem is to access the same code, more than one process may be competing, so that they have to cooperate and adjust with each other to access the code. But to share the data, the problem is every process may read or write the data, and if a process is writing the data and at the same time many other processes are reading the same data, it will still create a confusion. Therefore, process management is a problem which needs to be taken care of in shared paging. In shared code, if the code is getting shared inside between the processes, one copy of the read-only code is shared among the processes. In the shared code, this code should appear in some location in the logical address space of all processes, because many processes would be sharing this code. If the code is available in the code segment of a process 1, process 2, 3, 4 would never be able to access this particular code. Therefore, the code should be available in a common shared area. If the data is shared between the processes, here is the problem. Each process should keep a separate copy of the code and data. If it is a private code and data, the data is a shared data, the code is only kept as a private copy, data is kept in a common copy. The pages for the private code and data can appear anywhere in the logical address space, because it is a private property. If it is a public property shared among many other processes, it has to be kept in a common logical area. This is the example of shared pages. In share, you can see this is process P1 and this is the page table of process P1. This is process P2, this is its page table. This is process P3, this is its page table. And this is the actual real memory. The real physical memory houses every data and every information which is required by the process P1, P2 and P3. However, the page table is different for all these processes. Here the data 1, data 2 and data 3 are actually, data 1 is actually accessed by process P1, data 2 is accessed by P2, data 3 is accessed by process P3. However, ED1 indicates the code segment. Code ED1, ED2 and ED3 are shared by P2, P1 and P3. Therefore, from this figure, all the processes use the shared code. Every processes use its own private code. This is the example of shared pages. Implementation of shared pages may still require many other specialized hardware. However, the hardware which is available right now, the associative memory, the valid invalid bit registers may be insufficient for implementing the shared pages. In summary, in this lecture we have actually discussed about the paging scheme, address translation mechanisms, the structure or the visualization of a page table, and the free frames, how the operating system is keeping track of these free frames, the solution to internal fragmentation which we refer to as the associative memory or translation Lookaside buffer, the memory protection mechanisms implemented in terms of valid invalid bits, which is a mark of bit 0 or bit 1 among the frames, and the advanced mechanism of sharing the pages, that is in terms of sharing the code or sharing the data among the processes available inside your operating system. In the forthcoming lectures, we would discuss the variety of page tables available and the solution to internal fragmentation of your paging scheme. Let us now discuss few questions out of this particular lecture. What is memory access time? Can you introduce multiple levels of paging. Yes, multiple levels of paging can be introduced. How to increase the speed of page accesses? We have actually recommended 2 solutions for increasing the speed. However, mature solutions are available. Give a solution for paging in terms of varying the page size. If you vary the page size, it is called variable partition, or the blocks are called segments. The entire process now would be called segmentation, which we will discuss in the future lectures. Thank you.